Now, you said that, well, why can't I just look at the initial f prime and say, oh, it's an odd power, and therefore all of them are toggle switches? Why are you referring to just the zeros themselves?
Because technically speaking, this could be odd or even. It doesn't make any difference. I could still have all odd powers for these linear factors. I mean, just because this was an odd number doesn't mean all these linear factors can be raised to an odd power. I think it's completely independent. That's why I think you got to break it down to its factorization scheme, break it down to the linear factors, and then make a decision if you got zeros that are raised to an odd power factors.
Is there a way to do it like if you would have factored that first, like x squared?
You know, unfortunately, don't take this the wrong way. Before this week is over, I'm going to have a habit of coming in and factoring this piece completely. It's just that the zeros of the original function give me something else relative to the graph, namely x-intercepts. Not where they necessarily max out them in there. They could be the same, but in this case they definitely aren't. So I think factoring the original one gives it completely different conclusions. So everybody, I just built a sine graph of the first derivative function. Let's take a peek at what the heck it says for the original function. I think because my first derivative function is negative with this interval, my original function is decreasing, thank you, over the interval, then increasing, then decreasing, then increasing. But because my functions, the original function is defined everywhere, I think that necessarily means that at these two values of x, I yield local mins, and at this value of x, I yield the local max. So, to determine all local extrema, I've answered my question. F has a local min at x equals plus or minus 1 over root 2. And to answer my question directly, the relative, or local, excuse me, min is specifically f evaluated at plus or minus 1 over root 2. With this particular example, I have no idea. Is it negative 1/4? That was so appropriate. And f has a local max at x equals 0 and the local max specifically is f evaluated at 0, which is 0 itself. Do something else. Answer this question. Over what intervals is my function f increasing and decreasing? So increase, actually it's decreasing there, but increasing over all the way up to
0.
Do you want to include or not include the endpoints? I think you should, because I think my function is defined at those endpoints. And by the way, over
1 over root 2.
Very nice. Finish it up. And perfectly put. I think also f is decreasing over the interval from
Negative infinity to negative 1 over root 2.
Oh, hold, finish it up.
Bracket, or parentheses, bracket.
And over
0 to 1 over root 2. Close bracket.
Very nice.
If this question were on a test, would we have to do that?
And more.
Wait, for determine all local extrema?
I would ask determine all local extrema. Give me the intervals at which f is increasing and decreasing. Graph the darn beast. And discuss concavity. And maybe find something called inflection points, whatever they are.
Okay, but if it does just say determine all local extrema, then you wouldn't have to do that, right?
Correct.
Let's take a step back. And
Yes.
we said graph the whole thing. You mean, is that the graph of the whole thing?
No, that's just a sine graph. I mean graph the original function. Actually, can I ask that question next? Let's graph it.
Let's do that.
Let's do it. Can I erase this picture? We need it. Well, I need it. Actually, I won't erase it completely. I'll leave it there. I'll get rid of this. If I were to graph this function in the xy coordinate plane, here's the x-axis. Here's the y-axis. Question. How do you find x-intercepts? Set y equal to 0, solve for x. But since I've already factored my output, isn't it clear that the x-intercepts are going to be located at? Positive 1, 0, also at. Negative 1, 0, also at.
Zero, zero.
0, comma 0. I like it. How do I find the y-intercept?
Plug in zero.
Look at zero.
Yeah, it's the easy one. You just plug 0 in for x. Do you mind if I don't? Because we already just happen to have found it. It also happens to be an x-intercept.
Zero.
0.
And I think also I can build a sign graph for f. And if I were to build a sign graph for f, plotting the zeros of f, namely at -1, +1, and 0, I think I should test them to see where my y values are positive or negative. And if x is a billion, plugging a billion for x, everything's positive. Please stop.
No.
Please. Because I think this is 0 of a linear factor raised to an odd power. It acts as a toggle switch. Sign change. This is 0 of a linear factor raised, oh, look at that, to an even power. No sign change, no toggle switch. I think this value of x is a 0 of a linear factor raised to an odd power. Toggle switch, change signs. Does that mean I'm increasing or decreasing over 0?
Decreasing.
Which one?
Increasing.
Which one?
Increase.
Neither. Neither. It means what's positive? The y values. It means I live above the x-axis. And so I think I live above the x-axis to the left of the x-intercept -1, 0, and it's it's polynomial. So I think I have to behave something like this.
You turn the screensaver off, right?
I know, in that department, we make a really big deal that every single computer in this floor has the same image.
Yeah.
So I try not to mess with it.
And with the software they have on there, as soon as you restart it, it'll go back to normal.
Yeah. And my function has a negative y value between -1 and 0, so I know I behave like this. And don't do this.
No.
No. Actually, I come up, hit this x-intercept, I bounce back down because I'm negative again. And then I'm going to be positive to right of 0. Excuse me, positive to right of that x-intercept.
It doesn't necessarily matter how far down we bring the...
You know, in a sense, I think it does. Now, look at me, I'm sloppy. I didn't show you clearly where I dip down, but I don't have to because if I give you the points, the coordinates, then I think it answers the question. And look how lazy I am. I do think I got to look them in here and look them in here, but according to my first derivative function, sine graph, I change a negative to positive. In other words, f decreases then increases about that value of x. I think for free, the x-coordinate of that point is this. The x-coordinate of this point is this. Do you guys see I'm cheating? I'm not carefully unitizing my vertical axis. I don't have to, because I'm labeling the points of interest. Oh shoot, maybe I didn't.
You gotta find the y
To get the
value.
y value, when I plug that in for x, so I've already done that. Didn't I get a -1? And notice how this x-intercept is also a local max.
Well, how's the one on the right not -1/4?
It is. Don't you see it right there? See?
Okay.
That's negative.
Our math minors were on, sorry.
Something else. I'm a little sloppy with my picture. Do you think there should be symmetry with respect to the y-axis? How do you know that? They're all even powers of x in the original outputs function. And so I think it's an even function. There should be symmetry with respect to the y-axis. You guys, if I'm being accurate with my picture, can somebody just panic and say something about the relationship between this tangent line and the curve, locally speaking, about that point of interest?
Why?
Say something more about the relationship between the slope of the tangent line and green with the black curve, locally speaking. See, I think you say this. I think the curve lives entirely above the tangent line, except at one point. And because the curve lives entirely above the tangent line, I think something interesting is going on locally speaking. As I move from left to right, the curve has this upward concavity because it lives entirely above the tangent line. Actually, I think over the entire interval from -infinity all the way to a value of x close to here, every tangent line, locally speaking, lives entirely below the curve, or the curve lives entirely above the tangent line. I've got that upward concavity. I think up to a value of x, like somewhere around here, or up to this point in the curve, as you make your as you move along the curve in black, aren't the slopes of the tangent lines increasing? Up to that value of x, then the slope of tangent lines are decreasing. Up to that value of x, then the slopes of tangent lines are increasing. Maybe sometimes they're negative, sometimes positive, but they're always increasing. I think that should be my test for what I call concavity. Yes.
And you're just getting this from looking at it, right?
I'm just getting it from looking at it, but now I'm going to give you a tool that allows you to find out when this happened. It's exactly what it is. So test for what I call concavity. Number one, if f double prime of x is strictly positive over some interval I, f is said to be concave up. If, however, f double prime of x is strictly negative over some interval I, then f is said to be concave down. Well, at least over the interval. Oh, you guys, check out something kind of interesting at this local min right here. At that local min, what's the slope of the tangent line?
0.
0. Is my curve concave up or concave down there?
Up. The slope is.
I think this is one or the other. At this particular value of x, is my curve concave up or concave down?
Up.
I think it's concave up. I think the second derivative function looks positive there. This is so interesting. Check this out. If I got a point on my curve for which the tangent line is horizontal, but my curve is concave up at that particular value of x, doesn't that necessarily mean there has to be a local min?
Yes.
And if there is a value of x for which my derivative function is equal to 0, but my function at that particular value of x is concave down, doesn't that necessarily mean I have a local max there?
Yes.
Yes.
Let's put this in words. It's so important, I'll give it a name. Theorem. I'll call it my second derivative test.
Just real quick, and I know it's sort of picking straws, but don't you mean f is said to be concave up or concave down over I?
Over some interval I, yes, but I can also talk about my function being concave up or concave down at a given value of x. And I think at a given value of x, I'm concave down if at that one value of x, my second derivative function is negative.
Okay, so, but for the test for concavity, you meant to write.
Yeah, when I use that phrase test for concavity, I was talking about testing to see if I was concave up or concave down over an entire interval, but there's nothing wrong with me talking about being concave up or concave down at a specific value of x.
Okay.
So, theorem. My second derivative test. Let f double prime be continuous over some interval I containing C where f prime of C specifically is equal to 0. Number one, if f double prime of C is strictly positive, then f of C is a local min. If, however, f double prime of C is strictly negative, then f of C is a local max. Another man-made definition. If at x equals C, f changes concavity, then I will proclaim that the point C comma f of C is an inflection point. You guys, I know my picture's kind of sloppy. I know I can't draw. But don't you guys agree that somewhere around these two green points right here and here, I seem to be changing concavity? Doesn't it seem to be the case that I've got 2 points in green where I've got inflection points because I changed from being concave up to concave down, and then from concave down to concave up? Now, I know we've already found local extreme in my first example. Do you think we can re-answer the question, find all local extrema using the second derivative test, see if we get the same thing? So with the second derivative test, I guess what I've got to do is first compute my first derivative function. Oh, I've already done this. I forgot what I got because I erased it. 4x cubed minus 2x. Which factors? Nicely. So I got 3 critical numbers. But if I compute my second derivative function, doesn't that just simply give me, is that a 12x squared minus 2? Or shall I say, 2 times 6x squared minus 1? Or shall I say, 2 times root 6x minus 1 times root 6x plus 1, if I can write it? So building a sign graph for my second derivative function, I'll plot the 2 zeros. And I think these 2 real number lines subdivide the real number line. I think I misspoke with my words. I think these 2 real numbers subdivide real number line into 3 subintervals. I'm going to check them. If x is a billion, clearly all 3 of these factors are positive, so therefore the product's going to be positive. I'm done. Both these zeros are zeros of linear factors raised to non-power. I know they act as toggle switches. But that means my original function f changes from concave up to concave down to concave up. So I think my function's concave up over the interval from negative infinity to negative 1 over root 6. And from positive 1 over root 6 to infinity, I think it's concave down in the middle. I also think necessarily, that means, you guys, at negative 1, 6, or negative 1 over root 6, and at this value of x, I've got 2 inflection points. And so graphically speaking, I think that green point right here has a next value of negative 1 over root 6, comma something. And this point right here, this other inflection point, has an x coordinate of positive 1 over root 6. Are you guys with me?
No.
Oh, you don't like that. David, bring it on.
Well, what's confusing for me is those green points.
What about them?
Why are they kind of in the middle of? I understand that's where the graph goes from. No, I didn't get it actually. I thought I understood it for a second, but when I say it out loud, it makes no sense. The mins, local mins. Why aren't they the changing points going from negative to
Good point.
positive?
I think here's why. I think up to this green point right here, just anywhere to the left of that green point, if you draw any tangent line, isn't the curve going to live above the tangent line?
Oh, I see.
Now, I don't care if the tangent line has positive or negative slope. That's not what's important
Oh,
here.
okay.
I think the curve lives above it, therefore I'm concave up to that particular green point. And I think anywhere from here to here, I've got the downward cup shape, which means at any point the curve lives, locally speaking, below the tangent line.
Okay, that makes more sense.
Now are you happy?
Yes.
Oh, by the way, I never answered my question. My question was this. Can we use the second derivative test to find local extrema? Piece of cake. I think I've already found my critical numbers. So when I take my second derivative function and evaluate it at critical number, what was the first one? Negative 1 over root 2. I think I get this. I think I get 12 times negative 1 over root 2 raised to the second power minus 2. But jeepers, that's just 12 times 1/2 minus 2. Or shall I say 6 minus 2, which is this number, which is strictly positive. So, by the second derivative test, at x equals negative 1 over 2, we have a local minimum. Now, I know I've already established at a local minimum at that particular x value. I'm just coming to the conclusion using a slightly different test, the second derivative test. I think also that my second derivative function divided by second critical number 0 is equal to 12 times 0 squared minus 2, which is negative 2, which is negative. So, at x equals 0, we have a local max. By the second derivative test. You guys, I'm not going to write it, but same thing as the first statement. Since f double prime of positive 1 over root 2 is the same darn positive 4, which is strictly positive, by the second derivative test, I got a local min there. I have just answered a lot of questions relative to the first example. A lot.
So is this very similar to a test question?
Oh, absolutely. Oh yeah, you bet. You bet. Oh, my example's too
Easy.
yeah, he's just a polynomial. Let's get beyond this.
Yeah.
So, second example.
as hard as possible. Just kind of throw like the twistest thing you can think of, 'cause that's probably what's going to be on the test. So throw like another fraction in there, and
The twistiest thing that you can think of that's
So x plus 1 over x.
I can think of something really twisty.
yeah,
Just in between. So we do it in between first.
okay,
Can we do everything?
let's do it.
Just graph it, find local extrema, intervals of which are increasing, decreasing, intervals of which are concave up, concave down. Let's just answer everything.
Love it.
It's a rational function. Oh, I forgot. Before you guys came in tonight, you proclaimed your experts with pre-calculus because that's a prerequisite course. So, what does zeros my numerator give me visually?
Wait, your what is gonna
You are experts at pre-calculus. What's the zero my numerator going to give me?
2.
Well, 2 is a zero my numerator, but what does it tell me about the graph?
That it's, has an x-intercept.
Has an x-intercept at 2, 0. Can I put it in? I think if this is the x-axis, this is the, oh, I'll get bigger than this. Oh, here. X-axis. Y-axis. I think clearly at 2, 0, I've got an x-intercept. What does zeros my denominator give me? What kind of asymptote? It gives me a vertical asymptote. So I think at x equals -1, I've got a vertical asymptote. You know, in case the reader can't identify that, in case he's really groggy late at night grading your exam, you want to make it very clear to him that you've laid it good. And I think you and I can build a sine graph for the y values in this curve. To build a sine graph, I will plot the zeros in my numerator and denominator. And I think those two real number lines subdivide, the real number line into 3 subintervals we can check. If I plug something like 1 billion in for x, clearly everything is positive, and therefore the output of my function is positive. However, that is the zero of a linear factor being raised to an odd power. I get a sign change. However, that is the zero of a linear factor being raised to an even power. I do not get a sign change. How do I find y-intercepts? You took too long. You took way too long. Plug 0 for x. And when I plug 0 for x, I get...
-2 over 1. So -2.
0, -2.
Yeah.
Oh shoot, what have I just done? I found the x-intercepts, I found the y-intercept for this rational function, found the vertical asymptote. Oh, I got an idea. Let's find non-vertical asymptotes. How do I do that? Shift the powers
Differentiate it.
upstairs and downstairs. Since the degree upstairs is strictly less than downstairs, what do I have? I think I've got y equals 0 as a horizontal asymptote. And so I think y equals 0 is going to be a line to which I hug arbitrarily close to at extreme values of x. What if the degrees were the same?
We'd have a asymptote at, well, depends, it's a ratio of the coefficients.
Good. You'd have a horizontal asymptote about the line y equals c, where c is the ratio of leading coefficient upstairs to leading coefficient downstairs. What if the degree upstairs were exactly more than 1 downstairs?
You have an
You have
oblique
to actually
asymptote.
You have an oblique or slant asymptote, but you find it by looking at y equals q of x, where q of x is obtained by performing
Synthetic division.
or polynomial long division. I mean, I use synthetic division, I could, I just don't always, I'm not always able to use synthetic division. What if degree upstairs are more than, what if the degree upstairs were exactly 2 more than downstairs?
No asymptote.
Oh, but this isn't math 29 anymore. So what if the degree upstairs are 2 more than downstairs?
Increasing without bound.
Say this, perform polynomial long division. Your quotient will be a quadratic expression. Set y equal to the quadratic quotient will give you a parabola, and your parabola is now acting as the asymptote. It's a non-linear asymptote, a curve to which your curve is going to hug arbitrarily close at extreme values of x.
Are those called like parabolic asymptotes or something?
Yes. And if the degree upstairs were exactly 3 more than downstairs,
Cubic acid.
yeah, you get a disco function, because that thing is an asymptote. So I can play the game for any degree discrepancy between numerator and denominator. Well, I've hardly done anything, have I? Shoot. According to my picture, I guess in the left-hand side, to the left of this vertical asymptote, my y values are negative. So it looks something like that.
No.
No, I can't can't do this. I violated the vertical line test. Besides, look, I'm not hugging that horizontal asymptote. I'm not hugging this vertical asymptote. I'm way off base. These asymptotes are acting as electromagnets. The further and further you get with X and Y's, the more extreme they are, the stronger the electricity. So I think if I'm going to be hugging the horizontal asymptote, the extreme left-hand plane, I got to be doing something like this. And then maybe hugging the vertical asymptote by then. Now on the other side, immediately to the other side of the vertical asymptote, my y values are all negative. Until x becomes as big as positive 2, then I've got an x-intercept. Do I bounce back down or pass through?
Pass
I
through.
didn't know that.
Because of positive.
Because the y values are positive, so right at 2. Do you guys agree?
No,
No, I'm wrong. Why am I wrong?
because electromagnet.
Electromagnet.
Yes.
I've got a horizontal asymptote on the x-axis. I know my y values become positive on the other side of that x-intercept, but eventually I'm going to have to start coming down and hooking that asymptote. Do you think? Do you think? Talk about video game. Gosh.
Just see if it can work through the bubbles.
That would be awesome.
Challenge you.
Yeah, we'll work the math in the bubbles. Yes. There you go. Oh,
There.
yes.
Do you guys agree? I got a local max here. It doesn't make me dizzy. I probably have a local maximum around here and an inflection point right around here. Let's find them. To find the local max, I'll use the first derivative test. I'll compute my first derivative function. Oh, how do I differentiate that? Use the
Quotient rule.
quotient rule. Quotient rule says I have what's downstairs as is, don't touch. Times through the top. Minus what's up top, don't touch. Times through the bottom. All over the bottom twice. And x plus 1 squared is x squared plus 2x plus 1? I
Yes.
said x squared plus
Yes.
2. No, that's too much work. Instead, maybe I should
Factor.
pull out a factor of x plus 1. And with that one remaining factor on the outside, can I cancel with one of them downstairs?
Yes.
Yep.
But that merely leaves me with an x plus 1 minus the 2 times x minus 2. But that leaves you with a negative x of plus 5, all over x plus 1 cubed. I can build a sine graph. Plot to 0 my denominator and the numerator. Those are my two critical numbers. Because critical numbers are where the first derivative function is equal to 0 or undefined. I'm going to test them. Choosing something like 1 billion, plugging in for x. Don't you guys agree downstairs is positive, the upstairs is negative? The ratio which will be negative. Oh, I'm going to stop. These two are zeros of linear factors raised to an odd power. I get sign changes all over the place. Now, what does that say about the original function f? It says it changed from decreasing to increasing to decreasing. Oh, but that means in my picture, I'm decreasing to the left of the vertical asymptote? Yes, I am. I'm increasing the other side? I am. Until I hit this local max at 5 comma something, and I decrease again. How do I find the something?
Plug it back into the original.
So plugging 5 back in for x, what do I get?
Original.
A mistake.
Yeah, you
Try
go
to
into
find
the
a y
original.
value. I gotta plug back the original. Does that give me, I'm serious, I don't know, is that 3 over 6 squared?
36.
So isn't that 1
So
over
that's 1 over
13?
12.
1 over
right?
12, thank
Yeah.
you. By the way, if I were to write this out in words, f is increasing over the integral from
Negative 1,
Inclusive.
not inclusive. Inclusive.
because at x equals negative 1, the original function is not defined.
Yes.
And f is decreasing over the interval from
Negative infinity.
Parentheses all around.
And 5 to
and
infinity.
over, you said 5 to
Infinity.
infinity.
Including 5.
Including 5, yeah. Not including infinity.
Nice.
What kind of verbiage do you want to see on?
I think the way I'm saying it is just beautiful.
Okay.
You might want to write the word over so I can read it.
It's overrated.
It's
Well, if
overrated.
you write it like that, you should be able to read it, right?
So if we were given this on a test, is this, well, so far, is this what you would want to see?
Yes.
For intervals, if we put like, f is increasing over, whatever interval, and then we put just and then the other interval, is that fine too?
Yeah, I kind of love
Okay.
it. What I couldn't live with in the field is a unison.
Yeah,
That, I think, would be horribly mathematically wrong.
okay.
Now, to find the inflection point or to discuss concavity, I guess I need to come in and compute the second derivative function. And computing the second derivative function, shoot, you guys piece of cake. Let me just take this version of it. Differentiate using the quotient rule again. I get what's downstairs as is, do not touch. Times derivative upstairs. Minus what's upstairs. Times derivative what's downstairs. All over what's downstairs. Squared. I'm tired. I want to beat the clock. I'm lazy. I don't want to make any silly mistakes. So I guess I'll just pull out a common factor of x plus 1 squared from the top. If I pull out an x plus 1 squared from the top, don't I get to cancel 2 of them when we go downstairs? But if I pull out an x plus 1 squared from the numerator's position, at least in the first term, isn't this what's left over? And from the second term, isn't this what's left over? Or shall I say, I'm left with something over x plus 1 to the fourth. Is just the something is, I don't know, is it a 2x minus 16? Or shall I say 2 times x minus h all over x plus 1 to the fourth? Now I'm building a sign graph for the second derivative function. I will plot the zeros for my denominator and my numerator and see what the heck happens with signs. It affects his ability to clear that his first derivative function is positive. But 8 is a 0 of a linear factor raised to an odd power, so I get a sign change. Negative 1 is a 0 of a linear factor raised to an even power. I do not get a sign change, but this simply means something about the original function, specifically that the original function is concave down here, but concave up here. So I guess my inflection point is really located at 8 comma something. How do I find the something?
Plug it into
Plug it into the
Plug
original.
8 back in the original function, see what the output is. Don't I get a 6 over 9 squared? Which is a 2 over 27, I think. Well, double check my arithmetic, you know what I mean. And I think what this means in the end is that f is concave down over the intervals from negative infinity to negative 1 and over the interval from negative 1 to 8, but concave up over the interval from 8 on up. Notice I don't really include 8 as an endpoint in any of those intervals because I'm neither concave down nor concave up at that particular value.
You don't?
Well, no, because I think at x equals 8, I'm neither concave down nor concave up. As a matter of fact, David, if you drew a tangent line at that point,
Yes.
I think the curve's neither entirely above nor entirely below
Oh, I
some
see.
open interval.
I see.
So I certainly would be neither concave down nor concave up there. Oh, I still don't like my example.
Way too easy.
Yeah, I think so. I think so. Well, tonight I was able to get through 3 examples. That's really cool.
Something twisted.
About fraction of exponents.
Yeah, just
I could do that.
just
I think this
crazy.
could be just enhanced. Fine.
Oh,
I just-
Extrema
I want the nastiest thing on video so I can dissect it.
and inflection points. Are you ready?
Oh yeah,
Yes.
let's do this.
probably not.
Oy, oy, oy.
Yeah. That's it?
Oh, I think so.
Just throw like a sinusoidal in there.
I
Cosine
can
or
do that.
something.
I'll get there.
Negative sign, inverse sign, so.
Yes.
How do I find local extrema? Take the derivative and find out when.
It's equal to 0.
Well, no, see that again. Find out when.
It's increasing. Take the second.
Horizontal.
I could do that, but not, without the second derivative. How do I find local extrema?
Where it's increasing and decreasing.
You need to find the critical numbers.
Okay, I find the critical numbers first, which is where the first derivative function is equal to 0 or
Or
undefined.
undefined.
Undefined. Do you guys see my point? Okay. So let's say I compute the first derivative function. And if I already compute the first derivative function, I would use a product rule. And I think f prime of x is the derivative of the first. Don't listen to me. I said the derivative of the first.
Oh, X, I thought that's X.
Yeah, that's the next quarter. Times the second. Plus the first as is. Times the derivative of the second.
1/2.
Say it again.
1/2.
1 over.
1/2 root x plus 1 times 1. But,
Yes.
Wait, sorry, I got a quick question on the example before. Is -1 not part of our interval because it's a 0 on the first derivative, or because it's a 0 on the original?
Neither. Because the original function was undefined at x equals -1. Because at x equals -1, I had a vertical asymptote.
Okay, but let's say, there's like an undefined point on the original, but then it'd always be undefined
Exactly. Now, I think a better question to deal is this. At positive 8, I did not include it, but you know what? That wasn't at the location of vertical asymptote. I think more interesting is how I did not include 8, but 8 was defined, my function is defined at x equals 8.
Why not?
I don't include it because I think at that point I'm neither concave up nor concave down. Because at that inflection point at x equals 8, didn't my curve do this? The definition of inflection point is it's a point in which I change concavity. And I change from being concave down to concave up. But I think if you try to draw the tangent line to the graph at this particular value of x, then locally speaking about that point, I think the curve lives neither entirely above nor entirely below that tangent line. Thank you.
So
Tangent line
it's,
should be x equals 1, right? At any inflection point.
See, I think at an inflection point, the slope of the tangent line is completely irrelevant. It could be anything. It could be anything. Might even be undefined. Maybe I had this kind of curve. Hit that point and then change direction like that. I think I changed from concave down to concave up, but the slope of the tangent line at that particular value of x is not even defined.
Wow,
That can happen.
I've never seen that.
You have now.
Inflection point of something.
Yes, Ryan.
There's a couple examples in the book that I was confused about. Like it'd be like concave and then be like straight line. What do
You
do
mean
in that case?
concave like this and straight line horizontal, or
Or
concave and downward?
Yeah, either way. Like more like the bottom one's what I've seen in the book.
So, do you guys agree that this value of x, I got a local max? And hold it, you guys. This is a straight line. He said straight line. Am I strictly increasing over the interval from negative infinity to x of 2? No. I'm strictly increasing from negative infinity to x of 1, but then increasing from x of 1 to x of 2, and then decreasing after x of 2. But over what interval is my curve concave down?
Negative infinity.
to x1.
I can't hear you.
Negative.
I can't hear you.
Never.
Never.
Ever.
But it is concave up over
Oh,
Negative infinity to x of 2.
negative infinity to x of 2.
Okay.
And Ryan, I should be doing this because I'm not even sure what the question was, but I imagine those are the questions.
So would there be a point of inflection?
No, unfortunately, because I don't think at any point on the graph, I change from being concave up to concave down, or vice versa, concave down to concave up.
Okay.
So, by definition, there would be no inflection point.
This does not exist then?
Yeah, there is no inflection point.
Okay.
Just goes from being concave up to no concavity, right?
It changed from being concave up to no concavity, good way to put it.
Okay.
Will there ever be a situation where, when talking about intervals that are concave up and concave down, you use a bracket?
Now you got them thinking.
No,
No?
no,
Okay.
I cannot come with such an example.
Okay, cool.
Well, you guys, I never finished. My first derivative function looks way too,
Easy?
no, it's disjointed.
Unsimplified.
Uncivilized, unsimplified. Listen, fine.